Ready?
Yeah.
All right. Let's get started. And this is another CAN seminar we have today. And as part of our seminar series, we are turning back after two external speakers, or maybe three external speakers. We have one of our PhD students to give today's CAN seminar. Issam Kamia, PhD student at UIUC, who is actually working with me for about 2 years now. And after Issam came and joined our group, he has been working on multiple projects. This happens to be just one of them. But a little bit of background about Issam. Issam did his undergrad work in civil engineering in Palestine. Then his master's is from University of Wisconsin, Milwaukee. Worked with Professor Hani Titi. And then with his great recommendations, it was a great thing to hire him and bring him over to Illinois for sure, because Issam has been quite hardworking and effective. And as I said, he's been already working on multiple projects. So this happens to be one. This is a follow-up work on we did for North Carolina DOT recently on a model we developed for unbound aggregate routing. And he will give you all the information about that. So without further ado, I will just read the title of his presentation to you, Framework. And we call it framework because this is what we think the unbound aggregate routing model has to have certain components. That's how we developed this. Framework for developing an improved unbound aggregate based routing model for mechanistic empirical payment design. So,
thank you, Professor Tutumner, for the introduction, and welcome everyone to the CAN seminar. As Professor Tutumner already mentioned, today I'll be talking about the framework for developing an improved unbound aggregate based routing model for mechanistic empirical pavement design. I will start my presentation by acknowledging some of the collaborators and colleagues in this research, starting with Liang Chow, who was the former RA working on this project, then Dr. Deb Mishra, the former postdoc in Professor Tutumner's group, Dr. Judith Corley from the North Carolina Department of Transportation, and other students, engineers, research engineers, and technicians at UIUC and Illinois Center of Transportation, Erman Gungur, Hassan Kazmi, James Meister, Dr. Aaron Connon, Greg Rinshaw, and Mark Killian. So today we're talking about permanent deformation for unbound materials. And why permanent deformation? Because permanent deformation is one of the performance indicators for unbound layer materials in conventional pavement design for flexible pavements. And if we follow the permanent deformation cycles or rutting accumulation in unbound layer materials, then they actually go into 3 stages. Starting with the plastic shakedown stage, which is the fast accumulation of the permanent deformation at the start of life with the very few first load repetitions. Then the plastic creep, where the permanent deformation accumulates at a lower rate, and then the incremental collapse, where the permanent deformation starts to accumulate at a faster rate, and then the pavement will actually fail quickly from that stage. So why are we talking about permanent deformation, and what is the idea behind our research? So I'll start with what is existing now and what is the current pavement ME design routing model that is used. So this is the routing model that is used for unbound materials in the pavement ME software right now. And the model actually predicts the permanent deformation from some material properties and the resilient strain of the unbound layer, as well as the vertical strains and the sublayer thicknesses. And if you look at what this model and what is function of, you will actually see no stress states. But it is well known that stress states is one of the main factors that is affecting the routing of unbound aggregate materials. And actually, this model, there are some complaints from state DOTs and other people who are using this model, and they're saying that this model is actually predicting high permanent deformation accumulations that are not realistic in the field. And in our case, we're working with the North Carolina Department of Transportation, and they had this view that this model actually predicts 1/3 of the permanent deformation in their pavement is coming from the unbound layers when they run the pavement ME software design, while in reality their unbound materials actually don't rut much. And part of this is that because this model is actually calibrated using the data from the ASHO road test that was done here in Illinois. So talking about the model comes our research needs statement. So as I already said, the resilient modulus does not correlate strongly with plastic deformation for unbound aggregate materials, and applied stress states actually govern the permanent deformation trends in these materials. And the current pavement ME model that I just showed does not actually consider the effect of stress states, and usually it will predict high field rutting, and it will does not consider the contribution of the high quality aggregate materials because it does not consider the shear properties or the stress states. So talking about the current model now, this is the proposed UIUC permanent deformation model that we are trying to propose and validate and calibrate here. So this model actually has three parameters for which permanent strain depends on, which is the number of load cycles, the deviator stress or the stress state of the material, as well as the mobilized shear resistance over the shear strength of the material, which is known as the shear stress ratio. So if you see this model, two of the parameters are actually related to the shear strength and the stress rate. So this model actually accounts for the stress states in unbound layer materials. And just a quick overview of what the shear stress ratio is. So shear stress ratio is the applied shear strength over the shear stress of the material at any failure stress load, and we calculate after we know the Mohr Coulomb envelope for the unbound materials. So the project scope that I will discuss today is part of an North Carolina Department of Transportation project, which actually started with testing 16 crushed aggregate materials from different quarries at the state of North Carolina. And these 16 materials were tested at one engineered gradation here at UIUC for their shear strength properties and their permanent deformation properties. That was the original scope of the project. And then the extension scope of the project is actually for testing 4 of these 16 materials, which are, I will be referring to these much in my presentation, Fountain, Nash, Rougemont, and Goldhill materials from those different 4 quarries at the original or the source gradations to investigate the influence of their gradations on the permanent deformation accumulation. This is just a quick picture of the 16 materials that were tested, and the ones in red are actually the ones that we tested again at the source gradation. So we have Nash, Rougemont, Fountain, and Goldhill here out of the 16 different materials that were tested. Now, after I showed you the models, this is the model approach, or how we are estimating the permanent deformation in unbound layer materials. It's actually 4 steps. So the first step starts with selecting the aggregate materials and characterizing that aggregate material for its gradation, moisture density, because in our lab studies, we were doing everything at the optimal moisture content and other index properties and shape properties. The second step will be performing triaxial shear strength tests to calculate the friction angle and the cohesion of each material. And in order to do that, we need at least 2 shear tests at different confinement pressures, but 3 or more tests to get better correlation with the shear strength results. The third step is to perform a single-stage repeated load triaxial test. And for these single-stage triaxial tests, we were doing a 5 psi confinement pressure, which is a common value found in the field or in real-life applications. And we had different shear stress ratios calculated, and the material were tested at 3 different shear stress ratios, which are the stress to strength of 0.25, 0.5, and 0.75 values. And after we have all the lab data collected, we perform regression analysis to determine the model parameters that I just showed here, the A and B and C and D values from regression analysis. So as I said, this is a laboratory intensive works that for each material, it starts with doing some dry and washed sieving, moisture density curves, and unsoaked CBR, then the shear strength test, the permanent deformation test, and also this is not part of the model calibration, but we also did some resilient modulus tests for each material at the source gradations. Starting with the dry and wash sieving, I'm not gonna spend a lot of time on this, but we did test all the materials for their source gradations, and we did the dry sieving and the wash sieving, and we corrected the gradations to the wash sieving gradations. These are the 4 materials that I will talk about in particular, the Rougemont, Fountain, Goldhill, and Nash. The second step was the moisture density and CBR, and these were done according to the North Carolina DOT method, which is actually a modified compaction effort, where they use, instead of the modified one that use 56 blows, they use 86 blows. So they add another 30 blows per lift for each lift of the material in the moisture density test. And it is done in 5 equal layers, and the rest are as per AASHTO T180, which is the 10-pound hammer, 1.5 foot drop. And there was a minimum of 4 tests, and we also did the unsoaked CBR test performed for each of the samples. And here I'm showing the 4 materials for their moisture density curves as well as the CBR test. As you can see, most of the materials have optimum moisture content of around 5 to 6%, and maximum dry density in the range of 140 to 145. And they're all high quality aggregate materials, like CBRs are above 80 for all the materials at the optimum moisture content, unsoaked CBR, of course. And this is a summary showing the 4 materials that were tested at their source gradations. And this is the engineered gradation at which the 16 materials were previously tested. And this is a summary of the moisture density relationship, maximum dry density and optimum moisture content for the 4 materials at the source gradations. And if you see, all the materials tested at the engineered gradations had this gradation with 8% passing number 200. The source gradations were variable. The highest passing number 200 was 10.5%. The lowest was around 1.5%. And the gradations are quite different from the engineered gradation at which the materials were previously tested. The third step for the model is the shear strength test, and those are the monotonic triaxial shear strength test, 1% strain per minute, the regular sample size of 6-inch diameter by 12-inch height. And for each, we did at least 3 tests at approximately 5, 10, 15 psi confining pressure to get the Mohr Coulomb envelope, or the linear representation of the Mohr Coulomb envelope, and be able to calculate the friction angle and the cohesion intercept from these tests, which was done by linear regression analysis. And here I'm showing the summary of the shear test results for the 4 materials. Also, these are, most of them performed quite well in terms of shear strength. And this is the shear strength results shown. This is the calculation from the linear regression. And then these are the results for the source gradation and the engineered gradation. And if you look closely, you will see that there are some differences in the shear strength, like slightly differences for some materials, such as Rougemont, which has like 4 times the cohesion intercept, but these are both not too high. For fountain material, the other material we show source gradation had much lower cohesion than the engineered gradation. For Gold Hill material, which has plastic fines and plasticity index of 6, the friction angle at the source gradation, which has lower fines, was significantly higher than the friction angle at the engineered gradation, and the cohesion was a little bit higher. Same thing for Nash, pretty similar, just the source gradation had a slightly lower friction angle and a slightly higher cohesion. So after doing the shear strength test and knowing the shear strength of the materials, then we moved to the permanent deformation study or permanent deformation part of this study, where we used the University of Illinois FastCell device. And this device, I'm pretty sure many of you have seen it in the lab. It has a capability of doing the CCP constant confining pressure and the VCP variable confining pressure. But in this study, we're using it for the CCP mode, 5 psi constant confining pressure for all tests at different shear stress ratios of 0.25, 0.5, and 0.75 to test all the materials. For each material, we did 10,000 cycles. Each cycle is 1 second, 0.1 second loading, and 0.9 second rest period, which accounts for like around 3 hours per test for permanent deformation. And this is the FastCell machine that I was talking about, and this is part of the sample preparation and insertion inside the cell. So this is a custom-made machine, and it has a custom-made split mold to prepare the sample and before inserting it in the loading film. Now, this is a summary slide showing the permanent deformation trends at the different shear stress ratios, from the lower shear stress ratio shown in black of 0.25, 0.5 in red, and 0.75 in blue for the different materials. And as you can see here, different materials with different shear properties and different index properties show different levels of permanent deformation accumulation at the different materials. So some materials like Gold Hill and Fountain, for example, had similar levels of permanent deformation. And then other 2 materials like Nash and Rougemont had also similar levels of permanent deformation. Here I'm showing results and comparison of, so this one is the one I just showed was at source gradation, and here I'm showing the comparison between the source gradation and the engineered gradation that was used previously. And the engineered gradation curves are shown in dashed lines, while the source gradation ones are shown in the solid lines. And here you can see the applied stress state, or the sigma 1 values for source gradation and engineered gradation, as well as the differences in gradations for each material. So the black line in the gradation curve will indicate the engineered gradation, and the red line is the source or quarry gradations. And one thing to notice here is that at the lower shear stress ratios for at least 3 of the 4 materials, the permanent deformation accumulation is similar or less variable between the source and engineered gradation. But as we go to the higher shear stress ratios, then the variability is much higher. And this is expected because the loading is higher, and the variability in gradation will actually contribute to that difference in permanent deformation accumulation. So this is the results for the fountain material, pretty similar. Oh, computer is low battery. This is the result for the Goldhill material, which at the source gradation, it had 8% of plastic fines and showed very high levels of permanent deformation, while at the lower fines content for the source gradation, it actually showed significantly lower permanent deformation accumulation. And then similarly, the results for Nash material. As I also mentioned, we also did some resilient modulus testing on these materials, and we used the standard testing sequence for the T307 AASHTO standard, and we also did the resilient modulus test using the University of Illinois fast cell apparatus in the same procedure that was mentioned previously for the permanent deformation testing. And this is a summary of the resilient modulus test. And if you pay close attention, you will see that 3 of the 4 materials had very close resilient modulus trends, except for Goldhill, which had lower resilient modulus on the different stress states. But if you remember the permanent deformation curves that I was showing, they had actually different permanent deformation accumulation, which actually proves that PD and resilient modulus do not necessarily correlate very well with each other. And this is a summary slide showing all 4 materials at the source gradation and engineered gradation. Again, the dashed lines are for the engineered gradation, and the solid lines are for the source gradations. And based on the differences in gradation, you will see that some materials had high variability, such as Rougemont and Goldhill here, while other materials had pretty similar permanent deformation accumulation. Now, this slide actually shows all 20 materials tested, which are the 60 materials at the engineered gradation and the 4 materials at the source gradations. And these are plotted as the ultimate permanent strain at the 10,000 cycles versus the shear stress ratio level. And just paying close attention to the materials that were tested at source gradation. This is Goldhill, for example, lower fines content. We show much lower permanent deformation accumulation. Same thing for fountain here, the green curve, and similar level for Nash and Rougemont. Now, coming back to the permanent deformation model that I showed previously. So this is the model. And now, since we have all the lab data, we were trying to do the regression analysis and fit the model with the lab data to get the A, B, and CD values, and actually show how well this model correlates with the predicted lab permanent deformation levels. So running this model, these are the A, B, C, D values that we get from each model for the 4 materials showing at the source gradation and engineered gradation for each of the materials, and then the R-square values. So the R-square values are very high, but the problem here is that if you look closely at the A, B, C, D values that are obtained, for example, if you look at the A values, you will see values of 5 and values of 3 to the power minus 14. So there's a high variability and a huge range here. And if you look at the C and D values also, you will see some negative values in the C and D values, which is saying that if you increase your stress or the like apply higher loads or a higher shear stress ratio, your PD is actually decreasing, and this is not logical, and we will talk later how we tackle this thing. And just showing how well the permanent deformation accumulation predicted at the 3 shear stress ratios versus the ones that are measured in the lab are closely correlated. And as you can see, we have almost very high correlation between the permanent deformation measured in the lab and the one that is obtained from the predictions at the different shear stress ratios. Just to show how this model can be applied for pavement design or a practical application, we have a framework for the PD model application, where we also, oops. What happened? Turn. Sorry. Questions so far?
Did you run the compaction and the new gradation and the quarry gradation?
Yes. You mean the moisture density?
Yeah.
Yes.
What was the difference?
The previous results for moisture density were actually provided by NCDOT, and they were run at the source gradations. So we saw some slight differences between the maximum dry densities and the optimal moisture contents, but they were not very high. And those are the values that were used to prepare the samples for the engineering gradations that were previously done. So back to this step, I was showing the correlation between the model parameters or the predictions versus the actual test results. And I was talking about the application in real application for pavement design. So this actually starts like any other design where we select the pavement section, select our materials, layer properties, and layer thicknesses. And then the next step, because in our model we need the stress states, so we need to actually estimate the confining pressure and the deviator stress or the stress states at the mid-depth of the unbound layer material in the pavement design. So if you're using a design software such as Elipave or other layered elastic solution or any other program, we can actually get the stress states at the mid-depth of the unbound layer materials. So after we have the stress states and we have the shear properties of the material, we can calculate the shear stress ratios for these aggregate layers. And from the shear stress ratios, shear properties, and the stress states, we can do the model fitting at the required inputs that we need for our model. And this is just an example, design example for the model where we actually designed for a low volume road, moderate volume road, and high volume road. And the differences between the three is the layer thicknesses for the asphalt concrete and then the base course layer. So for low volume, for example, it's 3 inches, 8 inches for asphalt concrete and base course. And for the high volume road, it's 9 inches, 10 inches. And we actually incorporated the resilient modulus results here by using the stress strengthening or the stress-dependent resilient modulus inputs for the base course models. So we use the K theta model fitting for the resilient modulus results. And we assumed the typical values for the layer moduli and properties. So after running the example for the different materials, you will see that we get not only the rutting predictions in those materials at the low volume, moderate volume, and high volume roads, but we also get the shear stress ratios, which we calculated. And this is an important indicator because the higher the shear stress ratio, then the higher the accumulation of the permanent deformation in the plastic creep region that I showed at the beginning. and then the faster that the material is supposed to rot and fail. So it's expected that for low volume roads, the rotting level will be much higher because the AC thickness is lower, so more of the load is coming to the unbound materials. And also you can see the differences between the source and engineered gradations for the different materials, where the engineered gradations are shown in red and then the source gradations are shown in blue. And one thing here is that even though we estimated the stress states from the ELIPAVE program, we actually used sigma 3 of 5 psi to fit all the model, because this was the value that we used in the test. But we do have the sigma 3 values from the model running parameters. So coming to a related topic, but a different topic. So now that we have tests done for the two materials at the two different gradations, the source gradations and the engineered gradations, we were trying to see how well one model parameters will correlate to the permanent deformation accumulated at the other gradation. So just to simplify it, if we have the source gradation model parameters calculated, the ABCD values, and we are trying to estimate the permanent deformation accumulation for an engineered gradation unbound layer material, how well can we do that? So in order to do this analysis, we did two analyses that are similar in concept. For the first analysis, we used the engineered gradation model parameters to estimate the source gradations. For the other analysis, we did the opposite. We used the source gradation model parameters to estimate the engineered gradation parameters. And in order to do that, also, we calculated the shear stress values to be normalized with the shear properties at the model parameters that at which it was calculated. And the reason behind this analysis is to see the effect of applied stress states or the shear properties, as well as the gradation on the prediction of the permanent deformation at different materials. And if you see the results here, I'm showing here two materials and here another two materials. So materials that had different shear properties and significantly different gradations. Let me explain first what is this. So this 45 line is the measured and predicted are the same. This line here is the predicted, the measured, the permanent deformation is half the, the predicted is half the measured, and this one is the predicted is twice the measured gradation. And we set like this area in between these lines to show reasonable predictions of the permanent deformations. So for Rougemont, for example, where the gradation was significantly different, we will see that the source gradation were over-predicted the permanent deformation using the engineered gradations PD model parameters. For Fountain, for example, where the gradation was similar, they are within those limits. Gold Hill, again, the gradations was much different and the shear properties were much different, so they are off again. And Nash, they are within the range. This is the same thing done, but the opposite way around. The source gradation model parameters are used, and the same thing is shown here. If we use the source gradation model parameters for Rougemont and Gold Hill, then this time the permanent deformation will be underestimated, while for the other two materials it is still within the ranges. And this is shown here circled because when we normalize for the shear stress ratio, this point actually showed the shear stress ratio above 1, which indicates failure. This is Gold Hill, again, underestimated, and then Nash is within the limits. So after we did that, and we know that the model works and the model gives accurate predictions for permanent deformation, but we were trying to look at the ABCD values and the variability that we were getting in those ABCD values that I showed, the negative numbers and then the high ranges for these numbers. So if they are very variable, then the model is not robust. If they are negative, then something is not making sense. And we need to determine reasonable ranges for the ABCD values for which the regression parameters should lie within. In order to do that, we used forced regression, but before that, we were trying to see what regions are actually appropriate to consider the ABCD values to fall within. So in order to determine on the appropriate regions, we did several analyses, but we ended up choosing this one as the most appropriate and the one giving the best results. We used the results from the 16 different materials at the engineered gradation and the 4 materials at the source gradation, and we grouped those materials at so that the materials that had similar levels of permanent deformation were grouped together based on the ultimate permanent deformation levels, and then we run a regression analysis for all these grouped materials together. And the idea behind that is to have more data points for our regression run, so that we can actually get better correlation to the ABCD values. And here, these are the results before the forced regression. You already saw these results in the previous table, and these are the results for the other 12 materials. And these are the high variabilities and the negative numbers that we were talking about. And we believe that this is happening because we are trying to fit the model. So this is just an analogy to a polynomial fit. If you have this data points here and you're trying to fit it with a reasonable model, then if you use a polynomial with a low degree, then this might not be good. If you use like the third degree polynomial, this might be the fit we are looking for. If we use a high degree polynomial such as m is 9, then now we're picking all the points in the model. But actually, we have so many peaks that result in values that do not make sense. And what we are trying to do here is to get something similar to getting a proper fit of our model with the data. So this is the material grouping based on the permanent deformation levels of different permanent deformation levels, and we chose these material groups for the different 20 materials at the source gradation and the engineered gradation based on the permanent deformation levels that they have. And these are the results for the ABCD regression parameters from the grouped regression. So if you look at the results now, the A values are within good ranges. They're not very variable anymore. And the C and D values are always positive, which makes sense. And starting from this point, we chose ranges for the ABCD values to run the model parameters at using the forced regression. And if you look at the R-squared, then the R-squared values are also a little bit lower than what we were having before. But are they reasonably comparing with the field? I will show that later on. So these are the ABCD ranges that we determined based on the grouped regression. And then after we have those ranges, we actually ran a forced regression or an optimization code to on each material individually to obtain the optimized values for A, B, C, D regression parameters for those specified ranges. And those ranges can be also fine-tuned if we test more materials to determine more appropriate ranges if we need in the future. So these are the results for all the 16 materials. Now they're all within the ranges. And these are the R-squared values, which are reasonable. And just to give an example of how these forced regression parameters are comparing or are predicting the field or the experimental permanent deformation. So these are the predictions shown in dashed lines for the engineered gradation. And on the next slide, I'm going to show the source gradation. And if you look at these predictions, they're pretty good. They do actually predict the permanent deformation within good ranges, like Coulter, for example, and this is one of the most extreme cases. We have 5% or 5.1% at the experimental results, and then 5.5% prediction with the model parameters after forced regression. So these are actually good approximations. And here is the same results shown at the source gradations. And as you can see here again, also the predictions are very reasonable. Now, after we did the forced regression, we were trying to look at all the properties that we have for the materials and see how can we actually estimate A, B, and C, and D as functions of the material properties. Because we have those values, but can we actually predict permanent deformation for other materials that we don't test if we actually know the material properties of those materials by estimating the A, B, and C, and D values without needing to run shear stress and permanent deformation tests for each material in the lab. So we were looking at the different materials that we have. We were looking at the deviator stress values that were used at the different shear stress ratios in our lab tests, and then the shape properties, the angularity index, the surface texture, flat and elongated ratio. And this is also just preliminary. We just started looking at this recently, as well as the gradation properties that we have, such as the percent passing number 200, the coefficient of uniformity, coefficient of curvature, the D50, and other gradation properties. These results, as I said, are very preliminary, showing the effect of different parameters on the A, B, C, and D values. For example, if you look closely here at the A value, you will see that the value of A increases for all 4 materials that we have as the percent of fines content increases. especially for two of the materials, which are Rougemont and Gold Hill, where we see a significant increase. Value of B is not much affected, I would say, but still we have so few data points to actually make a reasonable judgment or decision from now. C value looks like it's decreasing, significant decrease at one point. D value is actually not changing with the percent fine content of passing number 200 for 3 materials, but is changing significantly for another 4 material. So we still have variabilities here, and I think the best way to go over this is to test more materials in order to have a bigger data set and be able to actually have good correlations between the effect of material properties and shape properties and stress states on the different materials. And this is just an example of something similar to what I'm talking about that was previously done by a PhD student in Professor Tutumler's group, Biwanji, who was actually looking at the resilient modulus model from MEPDG and trying to correlate K1, K2, K3 parameters with the material parameters or the material properties of the different aggregate layers. And in his case, he actually had 376 observations where he tried to get some correlations, and he actually got models for K1, K2, K3 as functions of the material properties with not so good correlations. But when he added the image properties or the shape properties, the flat elongated ratio and the surface texture, he actually got better correlations. And in this case, you have 115 observations. In our case, we still only have 4 observations, and we're trying to actually expand our data set so that we can do something similar to this. And this is pretty much what I'm talking about. If we have more data points, then we can have more robust predictions for our model, even if we go to higher, in this case, polynomial values, and in our case, even if we don't use a forced regression, but we use our normal regression parameter. And one future expectation is probably actually using a neural network where we can fit all our results into a neural network and then use that to predict the permanent deformation for the materials without actually having to run them in the lab. Just a brief discussion of what I went through over today. So we looked at the permanent deformation model that we had, and we saw that the effect of varying the gradation or the grain size distribution has a good impact on the shear strength properties, and especially if we have plastic fines, we see a significant difference between the shear properties. And this also has a significant effect on the gradation on the permanent deformation accumulation in those materials. And we saw that this difference is actually higher at the higher shear stress ratios and the lowest at the lower shear stress ratios. From the model parameters that we have so far, even before the forced regression, there was a very good correlation between the measured and the predicted permanent strain with the rotting model that is being proposed. This is the study of correlating the source gradation and engineered gradation model parameters to each other. So we saw that if the gradations are similar or the shear properties are similar, then one model parameters can actually estimate the other permanent deformation of other gradations reasonably well, but if they are not, then they will not. Shear strength properties using the calculation of shear stress ratio and the applied stress levels clearly dictate the permanent deformation accumulation trends in aggregate materials. And this is probably one of the main points, that the shear properties and the stress states are highly correlated with the permanent deformation, not like the resilience strain, which are not always very well correlated to that. Gradation was also seen to be an important property in addition to the stress states. And finally, for the forced regression technique that we used, then we have reasonable approximations when we did when we obtained those ranges for the regression parameters by the grouped regressions, and then these values can actually be fine-tuned because we are still looking at these right now. And we think that we need more data sets and more investigation to be able to determine the A, B, and C, D values as function of material properties and shape properties of the material. We show the ELIPAVE and UIEC routing model used together in pavement design, and we show that the model can actually be successfully used for an application in the design of unbound layers in pavement design. And finally, I will end with this slide, of our recommendations as future work. Of course, test additional aggregate materials using the established test procedure to generate more experimental data points in order to establish a robust permanent deformation prediction model where we can actually predict the model parameters using the aggregate properties. And then once we have a big data set that is big enough to predict the properties for other materials without being tested, then fitting the results into a neural network with more the data points to get a robust prediction for permanent deformation. Thank you very much for your attendance, and I hope that you liked my presentation.
I think you did an excellent job. Only 40 minutes, but you lost another 5 minutes on the way, 68 slides. Couldn't do that. Questions for Sam?
Very good work, Isam. I think it is like I expected. So this model that you have come up with, have you ever thought about reducing the coefficients to get a better fit? Have you tried other versions? Because it looks like, I don't know if this is the right term to use, but it looks like an overdetermined equation because you have two stress terms that are probably very correlated to each other, and then one resistance terms in the denominator.
That's a very, very good point. We actually looked at the model in the form of AN to the B, which is the more like the very most simple model the simplest model that is used to predict the permanent deformation. But this model is missing because if you look at AN to the B, then if you have different stress states, you are actually accumulating different permanent deformation levels. So you need another term that actually considers stress state. And we looked at the AN to the B, sigma D to the power C, and you actually get good correlations here. If you look at AN to the B with a shear stress ratio to the D only, then you actually also get good correlations. But if you cross out one of these terms, either the deviator stress or the shear stress ratio, you are actually missing something. And the reason of that, because if you have sigma D alone, then you are not contributing for the sigma 3 or you're confining pressure. And if you have the shear stress ratio alone, then at different shear stress ratios, like a shear stress ratio, let's say of 0.5, you can actually have so many combinations of stress states in terms of sigma 3 and sigma D. So both of them actually needs to be considered together in order to get good correlations. And that's why we think that
stress is like an indicator that will drive, let's say, your stress sigma D or tau F. They are both stress terms.
Right.
They are probably most likely very correlated to each other. When you really plot them, you will see maybe they're very correlated to each other in an experiment that you conduct. Maybe sigma D divided by shear strength. Have you ever tried that?
We never actually tried that. No.
Because at the end of the day, this is like empirical and phenomenological
Right.
model. We don't really look for too much physical, at least representation of this model. The terms have to make sense individually, what you put in there, but you're looking for the best correlation to something that you're looking on the left-hand side. Because this model, doesn't come from, any, theoretical, let's say, but it's just a phenomenological model. The terms just has to give the right direction to really predict the left-hand side number of cycle or left-hand side permanent deformations.
Yeah, let me jump here to say something. I know Isam made a good point, already said the things that are supposed to say, but in addition to that, a little more explanation, detail maybe to answer your question. So, first of all, just like with many good colleagues we have in Feynman Engineering who actually claimed about the same concept, the same point as a problem in this model before. Saying that why you're repeating the stress term twice? There's a redundancy here, and exactly your point. This is very good to catch. Indeed, that's something we were also worried about when we were trying out different combinations. Now, two very important things that contribute to permanent deformation are, first of all, the applied stress state. The second thing is the shear strength of the material, but the shear strength in relation to how much stress is applied. And that's, what kind of stress to strength ratio we're talking about, right? Those are the things that actually govern the permanent deformation accumulation. And if you drop tau F over tau max and go with sigma D only, all right, then you're taking into account just the applied stress, but you don't have any strength. If you drop sigma D because you think that sigma D is also in tau F, and it is, that's true, That's a good point. But then this eventually in the model comes up as tau f over tau max, which is a ratio, just like Issam was saying, 0.25 or 0.5, and that ratio can come up as the same for two totally different materials. One material that's weak, a very weak, high fines limestone, let's say, versus some of their granite material in NCDOT. They have a really good high quality material with little fines. And the ratio can come up to be the same in both materials. But their strengths are so different, so the amount of stress they can handle within a pavement system in the unbound granular can be quite different for the same amount of rubbing. So that you cannot actually just govern by a stress ratio term because the actual magnitude of the stress applied is not finally coming in the final PD calculation. So that's the reason both terms are needed. We went through this many times.
And what I was looking at
the
sigma d divided by strength, sigma d divided by tau max, but I'm sure you may have.
But that comes out as a stress ratio again. And the model takes that as a ratio.
Sigma d is an applied stress. You divide that by the strength, tau max. I think I'm sure you may have tried, but it looks like you find a way to make it work. That's the bottom line. I think that's what matters.
If you go to the Moore-Coulomb envelope, which is where actually it explains this best, sigma d is applied stress, okay? Right, sigma 1 minus sigma 3, right? All right, perfect. But then, what is actually going in that shear plane of the sample when the sample is about to break, okay? The shear strength mobilized on that plane, that's the highest shear stress, okay, that's supposed to be reaching 1, right? That's kind of the ratio where actually, as you go over 0.6, 0.7, you start to accumulate at a much higher rate permanent deformation. This is true for all materials, subgrade soils, asphalt, concrete, the same, okay? Stress dependency, and well, one thing missing on the left-hand side of that plot is that there is a specimen that somehow doesn't show, but, and then tau f is showing the mobilized shear stress on that failure plane, which is 45 plus P over 2, right? And that has to be compared with the maximum stress at failure, that is strength, under same confinement. That really governs how quickly you rot permanent, you accumulate permanent deformation and rot the pavement. Whereas sigma d is just sigma 1 minus sigma 3. I know related to tau f value, but by itself as a magnitude, it needs to come into the model as well. If we just use just the ratio, we couldn't make the difference between a weak material and a strong material in PD development accumulation. You cannot differentiate that. Chuck Schwartz made the exact same point that you made, and very good point, excellent point. And
I just looked at
going
from
after,
the fitting perspective. I'm not really, of course, knowing too much about the historical background. But another thing that I can comment on.
But models have to have variables in them
of course,
that make sense, that we now govern the behavior, right? And we know those two things directly impact. If you don't put them as stress term in the model, they come into the B, A, and to the B model, the simple phenomenological model, then A and B become stress dependent in that case. If you don't separate them out, put them as separately in a model. So,
but another point that I want to make now, the previous permanent deformation model was relying on strain. Now this model is relying on stress. Now if you really search plasticity theory, we need actually both of the terms. In the fundamental, let's say, theoretical plasticity theory for rate-dependent, rate-independent materials, you need stresses to decide whether you're going to fail or not, plus which direction that you're going to fail, the dilation or maybe normal dilation of shear type of plastic deformations. And the amount of plastic deformation is governed by the actually incremental changes in the strain. So actually, in one version of the model, we were heavily going on the stress. In this version, we are going on the stress. The question that I want to ask you is, consider a situation, for example, where you have a material, very high modulus material. You're applying very high stresses, but your tau max is average. Would you expect this material accumulate a lot of permanent deformations?
Say that again.
A very high modulus material, and you are applying a lot of stresses to this material, high deviatoric stresses. But average tau max, which can happen, modulus and strength, they are not correlated to each other. The average tau max, similar to one of your materials in here. Would you expect this material developing permanent deformations?
I wouldn't expect it to develop hyperpermanent deformations, but I would expect it to develop it at a fast rate, because if the shear properties are average, then if you're stressing the material with high stresses, then you're actually testing it at the high shear stress ratio. At higher shear stress ratio, if we come back to this curve, then you're actually increasing the rate of the plastic creep, and then you're moving to the incremental collapse stage at a faster rate than before. But I do agree with your point that probably both resilient properties and stress properties might be needed. But actually what we have right now is much better than what is in use for the PDG.
Just trying to understand. But why do you think the stress ratio will be affected by changing the modules, by having a stiff material?
Well, this was shown in, if you look closely at the permanent deformation results here, this is always shown. At the lower shear stress ratio, you have more flat curves. At the higher shear stress ratios, you accelerate the permanent deformation.
Stress ratio is something we apply.
Yes, but it's strength to stress to strength ratio. So as you increase your deviator stress or the shear, if you increase your stress states, the amount of stress you're applying, and you're actually stressing the material to higher limits than what it can actually tolerate at a lower strength levels.
You're basically bringing stress state close to the failure, static failure to the material. That's how you start to now repeat the loading at that working stress level that makes it more prone to rupturing, obviously, at higher rate. But then I think you did a good job in answering your question. Again, he's supposed to answer the question. Strain, all the permanent deformation models, if you look at in the past for subgrade rutting, granular material rutting, they're not meant for granular material rutting actually. But anyway, strain-based, like you said, Hassan. I think that's a very good point. And then if you look at how they come up with different coefficients and model parameters, then those values were all over the place. It's very hard to get a fix on strain level. Strain levels will change according to different pavement configuration and how thick they are and how they're loaded. And they're not robust as opposed to controlling stress. How much stress coming on top of subgrade, for example, as a subgrade rutting model, if you think it's just a strain-dependent, strain values in the different models, if you look at Asphalt Institute, Shell model, TRL model, or this and that, they're all over the place, the strain values. Stress is much better to control, and I think that's the reason why more and more recently the work with Carlos Gonzalez, who finished his PhD last May, Army Corps of Engineers lab, ERLIC down in Vicksburg, Mississippi, their airfield pavement division, they're shifting to using that more. Same thing is in the FAA's procedure nowadays, subgrade rutting, controlled by subgrade stress ratio, basically unconfined compressive strength divided by, stress divided by unconfined compressive strength of subgrade soil. So it's a more robust thing for us to, I guess, build into our models as for better predictions of PD. So that's how we look at it. But theoretically, what you're saying, 100% is I think, making sense and accurate. Strain and stress both need to be looked at from general perspective. The same is true, actually, interesting. When we talk about stress-dependent material behavior, and in pavement analysis, and pavement science and engineering now, I should say, okay, the way we take modulus as a function of stress state always for geomaterials, subgrade soils, unbound materials. If you look at geotechnical colleagues and your geotechnical friends, students in geotech area, go talk to them about, for example, their earthquake loading and other things, the small strain behavior. They're always relating modulus to strains. And if you look at some of the user material models in Abaqus and other general purpose finite element programs, those material models are all, Jacobians and things in the function of strain state, not stress state. right? That's because, again, coming from old geotech idea of making modulus as a function of strain. But a better approach is probably to include both stress and strain together. The same thing comes, I think, in the PV model. We need to probably move towards
For
that
our,
direction.
for our, maybe granular materials, especially combining stresses, may affect, of course, the behavior of the individual particles, but very, very present. Maybe we can discuss after the talk as well. Very good. Thanks.
Good discussion. Any other question?
Yeah, the other thing that we can not measure the position ratio of this material, you need to relate it to.
What?
To get the position ratio of the.
Poisson ratio?
Yeah, that's really hard to measure for granular material in the lab. That's probably one of the reasons that both the strain and the strains to be included in the models.
That's a good comment. You
Because
can
we
answer
always-
that, Isam?
You always assume that number, right?
Yeah, exactly. The number is going to be around 0.35 for unknown materials, but it's
Right.
actually very hard to
It's very hard to measure it, that what does that mean?
Well, in that sense, there's more complexity in the thing, actually. If you think about all of these, then the directional dependency of the behavior, right, and isotropy and everything else.
It can actually be measured, but it's going to be a hassle. Like you need the radial RVDTs and measured Gaussian and all this stuff. It can be measured.
Yeah, we've come up with a quite complicated, but I should say advanced, sophisticated model with anisotropic properties taken into account and everything for granular materials. Great studies with ICAR, Central of Aggregates for Research in Texas over the years. But what happened? Well, none of that got picked up and applied. We need to really
With a simple.
come up with something that is applicable, that can be actually used in a practical, these analysis and design framework, right? Penguin and other platforms should be able to use them. So, all right. Thanks a lot.
Thank you.